So we will start with the frequency shift key. So the topic here is this is coherent binary FSK. Okay, so this is frequency shift key. Correct, correct. Right. Whenever you are send, you are assume that let's assume that you have multiple symbols present, and each of the symbol is being sent over uh, different frequencies, right? Whenever we are it's like FM frequency modulation is present in analog version, whereas in the digital version you have what is called as a frequency shift keying. Okay, shift keying basically represents the digital modulation technique, and we are trying to change the frequency of the transmitted carrier wave whenever the message changes its amplitude. Okay, so basically we try to change the frequency of the carrier, right? Whenever the amplitude of the message signal, or in digital modulation it is a symbol. Okay, whenever the symbol changes. Right. It's like you in again in case of continuous modulation, you will have a band of frequencies representing for representation of the changes in the amplitude of the message signal. Message may change all the way from -2 volts to say +6 volts, right? For each and every continuous value that is present, right? Maybe we require a frequency, okay, that needs to be transmitted, right? Whereas when you see now, whenever we have a discrete case or the digital case, you may have only you may require, whenever you send zero, we want to send say a specific frequency, and let us assume that you want to send a second sample, and whenever you are sending the second sample like 1, you requires another frequency, say f2. Only f1 and f2 are required for us. All right. Okay, right. In other words, how many symbols you have for transmission, so many number of frequencies are required for digital. In case of continuous, you actually need a complete band rather than single frequencies, right? Whereas in digital, our requirement is the in terms of number of frequencies dependent on the number of symbols that you want to send. Okay, so for our discussion, we say that now we have only say two frequencies because we have only 0 and 1. They are the two symbols, right? But let's assume we go for a higher order of representation, not only bits. Let's say we club bits to get the symbols, right? 0 0 0 1 1 0 1 1, like this. If my symbols are 0 0 0 1 1 0 1, like that, if I at all I have four different symbols, right, then I require four different frequencies, right? So that's how it changes. Okay, all right. So now let us assume that the two signals b, we need to generate two different signals for representation of symbol 0 and symbol 1. Okay, so let's say that the s1 of t, this is equal to root of 2EB by TB into cos of 2 pi into F1 t. All right, so 0 less than or equal to t less than or equal to tb. This is what we require now, because this is f1 is the frequency of the first signal, or the one of the frequency, right? In this case, let us say this is for symbol 1. Okay, similarly, let's say I generate another signal s2 of t, and this s2 of t uh, is because of a different frequency for symbol 0. All right, this is 2 times the eb by tb. So you see the magnitude we try to keep same, and we change the frequency. So this is cos of 2 pi f2t. So this is 0 less than or equal to t less than or equal to tb. So this s2 is basically representing the symbol 0, right? Because 0 is one symbol for us, 1 is another symbol, right? So because of that reason, we try to represent both the symbols, symbol 0 by one signal, symbol 1 by a different signal. Now, the very basic characteristic of this particular, we have to choose the S1 and S2 in by using a criteria. Okay. First criteria, I should understand something. There is what is called as a TB, right? Uh, S1 means it corresponds to the choosing F1. S2 basically depends on choosing F2. Okay, so frequency 1 F1, when you choose, you actually indicate that you are choosing the S1, right? And when I say I have chosen some F2 value, that basically indicates that corresponds to the S2 signal, S2 of t. All right. Okay. Now, let us say we know, okay, let's just quickly write what is that. EB represents the energy of the transmitted symbol, or transmitted signal's energy per bit. All right. So EB represents the transmitted energy per bit, EB. So what is TB? TB will be the symbol duration. Okay, so that's the symbol duration. Now, F1 and F2 are the frequencies of both signals, S1 and S2 respectively, and we have a condition. The condition is that the F1 and F2 should be, right. Normally, what I say, the frequency is 1 by TB, correct? Normally, the frequency is 1 by the bit duration. But now you see, I cannot make both F1 and F2 same by choosing 1 by TB. Both cannot be 1 by TB. They have to be different, right? So how to make it different? You try to choose F1 and F2 in such a way that they are different integer multiples of 1 by TB. Okay, so uh, F1 comma F2, right, uh, should be integer multiples of 1 by TB. Now, how to make this happen, right? We choose using the following technique. So let's say f1 is equal to some constant n1, it's an integer, divided by tb, and choose the other one, that is f2, as some other integer n2 by tb. Okay, so here the n1 comma n2 are integers, and n1 is not equal to n2. Okay, the basic criteria here being, we take the f1 and f2 as integer multiples of 1 by tb, okay, and n1, the integer multiple both cannot be same, because when I say, if at all I make n1 and n2 same, it becomes once again the equal frequency. So I will not be able to do what I intended to do. Okay, right. So that's my objective here. All right. Now, there is another criteria. So whenever this happens, whenever the N1 and N2 are different, and F1 and F2 both are integer multiples of 1 by TB, I see the orthogonality coming into picture, correct? It's simply because orthogonality says that if you multiply a sinusoid with another sinusoid, okay, like sine of omega 1t into sine of omega 2t, where omega 1 omega 2 both are the integer multiples of its fundamental frequencies, right? What is the product? You get some answer, and when you integrate it over one period, the product becomes equal to 0, right? This is what we call as orthogonal signals, correct? So why we try to make f1 as n1 by tb and f2 as n2 by tb, and n1 and n2 are integer multiples of 1 by tb, because of this itself. Okay, I wanted to bring the concept of orthogonality. I just wanted them to be orthogonal. When we draw the constellation, this becomes more clear later. Okay, right. So this implies whenever whatever I assumed so far, right, is true, this is what is going to happen, right? Integration 0 to 1 bit duration TB, take any S1, I'll just write Si of t into Sj of t dt. If you integrate, we have two answers. First answer is 0 whenever I is not equal to j. Whenever you take a product of two different S1, S1, S2, or right, like that, S2, S1, etc., it becomes equal to 0. And the product becomes equal to EB, right, provided I is equal to j, right? This is something like cos of F1t into cos of F2t, right? Instead of doing that different frequencies, you make same frequency, F1 into F1, right? Cos square of F1, right? That's what, when both are same, it simply becomes a cos square function, right? So cos square function is basically, you can see that, right? It will not cancel. The whole area under the curve is not 0. That's why you have answer EB coming up. If at all it is equal, right? If they are uh, equal, means it will cancel out. Whatever is the area above the x-axis and the area below the x-axis, integration will make cancel them. That's why it will become 0. All right. Okay, so we know this concept, right? So this implies this condition is satisfied, indicating that S1 and S2 are orthogonal, right? So this means the S1 of t and the S2 of t, right? They are orthogonal. They are orthogonal. Right. So for orthogonal signals, I have to have orthogonal basis function, right? So now it's very clear that we require two different functions to be generated, S1 of t and S2 of t. And also we understood that both of them, we expect them to be orthogonal, right? So the next idea is to generate the phi values. So we try to generate the phi1 and phi2. Obviously, we require two because both are different functions. S1 and S2 are different in terms of their frequencies, right? So because of that, now we try to generate two different basis functions, right? Again, they become orthogonal now. They are orthogonal and unit energy. That's why we can call them as orthonormal functions, right? So let's try to generate the orthonormal basis functions required. Therefore, the ortho and normal. Okay, the orthonormal the angle between the two orthogonal functions we are writing is 90 degree. That's why they are called as ortho and normal. Normal because unit energy, ortho because they are going to have the angle between them, if we try to write in a vector notation, is 90 degree. All right, so orthonormal basis functions required are as follows. So first one is say phi 1 of t. Phi 1 of t will be, this is equal to root of 2 by tb into cos of say 2 pi f1 t. This is between 0 to tb, 0 less than t less than equal to tb, and this is 0 else. This is the first function which we are going to use as a orthonormal basis function, and the second function, that is phi 2 of t, should be equal to, this is root of 2 over tb cos, right, 2 pi f2t, 0 less than or equal to t less than or equal to tb. Okay, so this is 0 else. Right. Now, the functions are chosen in such a way that we can try to represent both the required symbol functions, that is s1 of t and s2 of t, using these two functions, phi 1 of t and phi 2 of t respectively. That's our idea, right? So in all the previous cases, we have done the same thing, but there we had only one orthogonal function. There is no normality coming to picture, right? Because only one function was sufficient to represent the whole set of symbols in those modulation techniques, namely ASK and PSK, correct? But in this case, since we require two different frequencies to be generated, right? So we have no other option but to use two different orthonormal basis functions. So we have declared them as of now. It's phi 1 of t and phi 2 of t. Phi 1 has an amplitude of root of 2 by tb with a frequency of f1, and we assigned a cosine function for that. And the phi 2 of t also has the same or magnitude, that is root of 2 by tb, and it's a cosine function with the frequency f2, right? So this implies, in the next step, our intention is to represent the s1 of t and s2 of t in terms of the orthonormal functions we assumed. So s1 of t becomes equal to root of eb, because this is the energy of that symbol which I want to transmit, into 5. All right, and the s2 of t can be represented as, this is root of eb into phi 2 of t. Yes, so both the symbols, symbol 1 and symbol 0, will have the same energy or same amplitude out of eb. Okay, root eb will be the amplitude of both the symbols, but we have to observe one thing, that since phi 1 and phi 2 are different, they are going to have different frequencies. This is what is. So as you change your symbol from 0 to symbol 1, ultimately you can see on a graph which we are going to write now itself, we will be observing that the frequency will keep changing. You are actually frequency shift keying, which means you are shifting the frequencies whenever you change the symbols. Symbol 0, some frequency, symbol 1, some other frequency. Amplitude remains same. Okay, all right. Now let's directly write a graph indicating what's going to happen. All right. So let's try to, okay, let's try to bring the plot. Okay, this is the plot. The x-axis will become the time t, and the y-axis is the magnitude, right? I'll simply write s of t, because either the s of t will be s1 of t or s2 of t, right? And let us say we want to use the okay, I want to send, let's say, 1 0 0 1 0 1. This is what I want to transmit. Assuming that the gap between each of these vertical lines is the symbol duration, that is 1 by t. And since we are using that 1 by tb as our basic number, whose integer multiples are being used for generation of different frequencies, correct? F1 and F2. So let us write the maximum amplitudes of this sequence. Like this is the maximum on the positive side, and let's assume this is the maximum on the negative side. Now, so for one, right, I use a specific frequency, say it's a low frequency signal, let's assume. Okay, I just have like this. Okay, and for the 0, let us assume I'm using a okay, let's go for a high frequency signal. So this actually has more oscillations. Okay, so you can see, let me try to write it. Changing the frequency, you can see that this signal has more oscillations. Zeros have more oscillations compared to ones. Okay, once again the same thing I want to show here. So whenever I write a 0, I'm continuing with the same signal. Okay, I'm not changing the frequency. Frequency remains same, right? But when signal changes to 1, now you see it's a low frequency signal, right? So the number of oscillations are less. Whereas 0 has more oscillations, right? So I'm getting more peaks for signal. Once again, I have 1. So you can see it has less number of oscillations compared to. So frequency is different. That's what is the ultimate thing to note. So all the red plots have frequencies f2, some different frequencies compared to the blue colored wave. Okay, let me write the blue colored waves over here. This is f1. So this has a frequency f1. This has another frequency f1. The third part also has a different frequency f1. So it's very clear that when we are uh, trying to shift the frequencies depending on what is the symbol that is being sent, right? So this is called as frequency shift key, right? I'm actually shifting the frequencies depending upon what is the symbol that is being sent. Again, it's very clear that from this graph, depending on the number of symbols we use, right, the number of required frequencies will also change. So we wrote S1 and S2 in terms of phi1 and phi2 just now, correct? So S1 of t is root EB into phi1 of t, S2 of t is root EB into phi2 of t. where phi 1 and phi 2 are different uh, orthonormal basis functions we have chosen for this representation. Right. Now, you see, any FSK signal can be considered as two different ASK signals, right? Why? I'll tell you. If you look at the ASK, right? So just go back and check the ASK concept. ASK is actually only this part. This one is one ASK. S1 of t is equal to root EB into phi 1. Other one is 0, correct? Similarly, you can call that as S1 dash of t, which is a 0. Okay. At the same time, S2 of t, which is completely different ASK with phi 2 of t as its uh, orthonormal function, right? Phi 2 of t is its basis function, right? So you have root EB into phi 2, which is one symbol, that is S2 of t, other symbol being 0. Are you okay? But now you see the phi 1, how we wrote the phi 1. When I consider the ASK, right? The phi 1 was written along any axis, right? We simply took it as x-axis and we plotted, but we never knew that is it only x-axis, why not it be y-axis or z-axis? Could be a question, correct? You can choose any axis, right? And you can plot, correct? So what we try to do now is that symbol 1 is represented by a sinusoidal signal whose frequency is f1 here. That is for symbol 1. Similarly, symbol 0 is represented, right, by a different what you call ASK signal. If we try to consider in that way, the analysis of FSK becomes very easy for us. Okay, so let's try to do that now. Let us try to write the above two equations in different type of signal space, right? Since we have two different phi 1 and phi 2, we have two different axes coming into picture. Why? I'll tell you now. So let me draw the axis first. So I'm trying to write the constellation diagram first. Okay, so the constellation diagram can be represented by using two different axes now. So this is for phi 1, this is the phi 2. Okay, we have phi 1 and phi 2 like this, and let us try to represent, see, phi 1 as one of the ASK, right? How we wrote ASK? If you remember, ASK had two values, one is 0 and one is root of EB, correct? This is first ASK, let's assume, and it can be plotted anywhere, we know that, right? And the phi 2, I use a different axis and I'll plot the, what you call, say, this is EB now, right? So second signal has a different frequency, but this is root EB. Now actually what happens is like this. This is because I'm, oh, it has to be, this particular plot is called as the signal space or the constellation diagram. So this is the constellation diagram that I'm, so you can see that the points that we have marked over there are actually root EB comma 0, and the second one is 0 comma root EB, because that's present on the different axis, y axis. Now we'll show you the orthogonality as well, but before that let me show you, this is point number 1, this is the second point, and actually I need the decision boundary, correct? The decision boundary is somewhere at the middle, at the center, and this is how it's going to look like. And the easiest possible solution to think of is okay, let me write here. This is the decision boundary, that is x1 equal to x2 or phi1 equal to phi2, right? So y is equal to x is the straight line. That's this red colored straight line. On this side, on the right side of this boundary line, we are going to call that region as, say, this is region 1, Z1. On the other side, this side, whatever region we have here, this will be the region, say, Z2. So on one side, if at all the signal falls on the sample falls on the left hand side of this decision boundary, it belongs to region Z2, and anything that falls on the right side belongs to the region Z1. Okay, but the main points of our interest are like this. Again, I'll try to connect them, maybe using a straight line. Okay, so connect just like this to understand. Okay, this is what we are looking for. Either it's over here or it's on this side. They are the main points used to make or identify the decision boundary. Okay, now in order to plot these samples, right? So how did we plot them along phi2 or phi1 specifically? We'll be able to answer that now. Okay, for that reason, let us try to represent the coefficients of S1. Okay, whenever we are trying to plot S1 over using phi1 and S1 using phi2. For example, this is what we know, the coefficients of S1 of t, right? In order to calculate that, we can what we can do is we can simply use the following equation. S11 is equal to integration 0 to tb. Take the first signal, that is S1 of t, and multiply it with phi1 of t dt. What is S1? I know it is root of 2eb by tb into cos of f1, right? Cos 2 pi f1 t. And what is phi1? It is simply root of 2 by tb into cos of 2 pi f1. Correct? So this is equal to, now what you do, actually we can do the integration, but I'm going to skip as of now. This comes as simply root eb. Okay, S11 is S1's image on phi1. Okay, it has a coefficient root eb. Now let me calculate the S12, which is nothing but integration 0 to tb S1 of t. Anyway, you have, instead of phi1 you should use phi2, because I'm trying to calculate what is the image of this S1 point, S1 signal on phi2. Okay, so phi2 dt, this comes to be, you know that S1, and when I multiply S1 and phi2, basically I'm trying to multiply cos of 2 pi f1t into cos of 2 pi f2t. So that's product is 0, right? I know that. When you take a product and when you integrate, it's 0. So directly this becomes equal to 0. So this means my points are root EB along phi1 axis, 0 along second axis. You see, that's why we plotted this one, correct? You see, root EB comma 0, that came from here. And we will calculate the coefficients of S2 now, okay, in a very similar fashion. Coefficients of S2 of t. Now instead of S1, we use S2 inside the integrals. So this is S21. S21 is equal to integration 0 to tb S2 of t phi1 of t dt. Using the same reason, right? S2 and S51, when you multiply, we are basically trying to multiply the two sinusoids of two different frequencies, and the product integration results in 0. So this is equal to 0. So it's something like the image of the second uh, function S2 on the first basis function is 0. Right. Actually, I'm coming to know this is the orthogonality is being used only after seeing this. But without doing this, if I directly say that it's orthogonal, it doesn't mean, right? So there is no meaning for that. So I'm just trying to give the quick view of how the orthogonality is, which we considered earlier, right? How we are using it over here, I'm showing like this. Okay. S22 is equal to, yes, see the concept of orthogonality is like this. You take two different signals, preferably sinusoids of different frequencies, and the frequencies are integer multiples of the fundamental frequency. Like you consider some 1 by TB as your frequency, n1 by TB is my first frequency, n2 by TB is my second frequency. Okay, so we use that now to initially we consider that, okay, because of this they are orthogonal. Now we are justifying that. All right, so S22 is S2 of t into phi 2 of t dt. Now you see, when I say S2 of t into phi 2 of t, S2 of t has a cos of 2 pi f2t, and phi 2 is also cos of 2 pi f2t. It's actually cos square. There is a cos square function. Cos square function, whenever you integrate, you have an answer coming up. Okay, because the product, the area under cos square function is not 0. Right? So because of which I have an answer. So when we do this integration, we are going to get the answer that is equal to root of EB. Yes, so you see the coordinates are 0 comma root of EB. Along y-axis I have this. So you can see now this 0 comma root EB is here. So along one axis it is 0, other axis it is root EB. Alright, so we have the 2 points denoted by root EB comma 0 for S1 of t, and 0 comma root EB for the S2 of t. Ultimately, we got them. Okay, so this is how we always try to represent uh, the FSK symbols on the constellation diagram. Okay. Now our next intention is to see the block diagram representation of the modulator first, then we'll go for a demodulator. FSK modulator circuit. We start with the binary wave. When I say binary wave, I am talking in terms of ones and zeros. Okay, this waveform, whichever is the input, basically it enters into the circuit by two different channels. Okay, so the first channel is getting multiplied with the phi 1 of t. Okay, so I'm multiplying phi 1 of t is equal to, that is root of 2 by tb into cos 2 pi f1t, right? So I'm going to call this as the one part which goes to the top of the block diagram. We'll try to represent this as say m of t. M of t could be like either I'm sending root EB as it is, or I may send a 0. Okay, this is what goes to the top. At the same time, I use another what you call another path or another channel to my block diagram, but this is inverted. Okay, there is an inverted because 1 should become 0 and 0 should become 1 for us. So here I am going to multiply this part with the phi 2. Okay, that is root of 2 by TB into cosine of 2 pi f2t. Here, why we use an inverter is because of the one fact that whenever symbol 1 goes into the circuit, it should get multiplied with phi 1. Okay, but when phi 2 comes, right, but when 0 comes, you cannot simply multiply 0 into something. It has to be converted into 1, right? So that's why I use an inverter to convert zeros into ones, right? Since the original symbol is 0, 0 gets multiplied with the phi 1, that results in 0. So upper part has no meaning for when 0 enters. Okay. Similarly, when 1 enters into the circuit, the lower part of the circuit has no meaning because its 1 becomes 0 using the inverter and that gets multiplied with phi 2. Okay, so what exactly happens here? I'll try to write this as m, maybe it's a m dash of t or m bar. This actually passes when eb root eb goes on from the top. This passes as 0. So this is 0 or root eb. Okay, just note a difference. This is root eb or 0. This is 0 or root eb. In the sense, whenever root eb goes on the top line, it passes 0 at the bottom. Correct? Whenever the top line is 0, the bottom line takes root eb. That's what they are equivalent. Okay, because of the the inverter that is present over here. Okay, we got these two. So the top part of the circuit generates S1 of t as a result. So I'll call this is S1 of t, and the bottom part of my circuit produces the other signal required, which is S2 of t. So one of them will be 0, both of them will not exist simultaneously. That's obvious because one of the symbol will be 0, right? So I can directly add them without having any effect of one on the other because one of them will be 0, right? When other one exists, when S1 of t is there, S2 will be 0. When S2 of t exists, S1 of t will be 0. So simply we can add them to get the BFSK denoted as some S of t. All right, so that is the modulator circuit of the FSK. So now we will move on to the demodulator circuit. Okay. This is FSK demodulator. So let us say we received some signal. Correct. So let us assume that there is some antenna. Okay. So this picks up some signal, and let's denote the received signal as x of t, because we don't call it directly s of t because of the fact that the s of t, when you send from the transmitter antenna, this is s of t, but the channel will definitely change it by adding some noise, right? So because of the addition of noise, right, expected some definitely it's going to add a noise, right? So the noise plus s of t is x of t, which you pick up on the receiver side. Okay. Yes. So we write it as x of t. That's a received signal. Again, we split into two channels. So since it is coherent detection, one of the part will multiply with phi 1, okay, and the other part will multiply phi 2. So phi 1 of t and phi 2 of t. So as soon as you multiply, I have to integrate 0 to tb. This is what is going to happen on both the sides. Okay, and when I have both the, because one of them will exist once again, right, by default, both of them will are not going to exist. They will not be present at a given point of time, so you can simply club them together, right? So what we do, we try to this plus the lower half is minus. Okay, so let's say this is x1 and this is x2. So we have y coming up, and we use this y to make a decision. Okay, so decision. Okay, let's make the decision in this way. So this is the decision making circuit, and for making any of the decision, you need a threshold. Say VTH equal to 0. So let's look at the threshold now. So in what way we are going to make the decision, that depends on this. We have a binary wave at the output. So this will be 1 or 0 dependent on the following. So see, if this is 1, this is 1 under some cases, this is 0 under different cases. Okay, so we have to use the what you call the threshold, correct? So whatever threshold values we have to use the threshold to make this decision by default. Okay, so let's do this in this way. It is 1 if y is greater than or equal to 0, if this is 0 when y is less than 0. Okay, so that's how we use the decision. So a series of ones and zeros will come at the output dependent on what value of y has been received, and whether it is greater than 0, output is 1. If it is less than 0, the output becomes equal to 0. So you obtain back your sequence. See, the next topic is the probability of error. So for coherent FSK, the probability of error PE is equal to 1 by 2 error function of, this is root of EB by 2N naught. So we can actually make a comparison of these expressions for probability of symbol error of PSK and FSK, right? It's very clear that we have to double the bit energy for FSK, right? Because you see the 2 was there in the numerator, now it has actually entered into the denominator. So there is a proof for this as well, right? But anyway, our intention is not to do the mathematics, right? Just to understand the concept, I think the equation is sufficient. All right.